observation to find their trajectories, and then you can continue tracing their positions. So in the sense that classical mechanics gives you a very satisfactory way of dealing with the world around us. That you specify initial conditions. Initial conditions mean initial velocity, initial position, and we know Newton's laws of motion, and then we can predict with infinite accuracy what would happen later on, where would the particles be. For example, if you can specify the position and velocities of planets around Sun at today, you can now predict their position and velocities for the rest of eternity, right? Because there's no ambiguity in the equations of motions and the use of Newton's law. They are deterministic. You tell us now, and we can tell you later where will they be and what will be their velocity. But in quantum physics, we now have learned that particles are found at a place at a given time, but it has uncertainty associated with it. For example, momentum and position, they have certain uncertainties with them. So it means that once the particle is here, if it was supposed to be in this delta x region, here it might be in some wider region. So you don't exactly know, but you even probabilistically, if it was somewhere between here and here, now it is somewhere between here and here. So you can still kind of predict probabilities, you can propagate them, but for them to predict, you need the wave functions. So far, we have dealt with only free particles, which were not truly free particles, but we approximated them as free particles. So the next important question is, and which we are going to be dealing with in most of the rest of the course, is how to find the wave functions of a particle in a given situation. Because once you know the wave function, you can find its probability of existence. For example, if I tell you the wave function psi of some particle, you can take its absolute square, and we know the probability density is proportional to that. And you take probability square, probability in this region, you can find probability in this region, and so on. You can find the probability of average position and other things. But this one question that we have to answer, and that is that what is the wave function associated with particle? And actually, it took scientists about 10 to 15 years to figure out. In 1910s, 12, 13, 14, 15, it started to become clear that the physics that is applicable at the microscopic scale is different from macroscopic physics that we are used to. So people began their work on finding the new physics and finding the new laws of physics. And two people actually became successful before everybody else in 1926 and 27. So one was Heisenberg, who developed a matrix mechanics, where you deal with particles in an infinite dimensional space, and you construct their matrices and probabilities and so on. That is something that we are not going to be discussing in this course. It's called matrix mechanics. And completely equivalent approach is what is commonly referred to as wave mechanics. With essentially they're both exactly the same. They give same prediction, so they're same physics. But the wave mechanics is a bit easier to handle at the beginning stage, and it is even though it's still different from the classical physics that we have studied, but it's little bit more intuitive because of your little experience with waves. So that's what we are going to study. So the wave mechanics, which was invented by, not invented, but I should say discovered by Schrodinger, that's what we are going to discuss. And in this lecture and the next 3-4 lectures, we will be learning how to find the wave functions associated with particles in different situations. We will actually discuss only 2 to 3 basic situations in which we can find wave function on the board, because the scheme will be applicable to every situation. For example, you want to find the wave function associated with the sodium ion present in one of your neurons, and you want to predict how the sodium ion will go. You can of course use the same Schrodinger equation to find the wave function and predict the behavior, and you can extrapolate and also work out how different neurons will interact. But for that, you need a computer to work it out. So that's something that we will not be discussing. So idea in this course is to give you basic tools and tell you how the wave function is obtained, and we will mostly work with problems where we can find the wave function by hand. But for complicated problem, you can do it on computer. Some of you will do in your higher classes. And then once we have a wave function, we will learn how to extract information from it. Unfortunately, we will not be doing one thing in this course, which is very interesting, but it's actually very advanced. And that is that if I give you wave function of a particle now, a particle which is, let's say, present between the slits, and I ask you where the particle will be or what will be its wave function after, let's say, 10 seconds, that's the propagation of the wave function. That's the part that we will not be attempting in this course. So we will be working with simple things, but I'm telling you what we are not doing, because you should know that how little we are learning in this course and what are the stuff that is left behind. The second thing that we will be doing is this, that this wave mechanics that we will be studying is sort of an extension of classical mechanics, not including the relativistic mechanics. हमने इस कोर्स के शुरू में स्पेशल थ्योरी ऑफ रिलेटिविटी की थी, कुछ जनरल थ्योरी भी की. So there is a quantum theory which includes special theory in itself. So that relativistic quantum theory we will not be studying in this course. हम इसमें जो basic quantum theory है, which you can in some sense say is the generalization of Newton's second law. That's what we will be studying in this course. Okay, so coming back to Schrodinger, he was the person who discovered how to find the wave function associated with different particles. And he gave an equation which is now called Schrodinger equation. I'm first going to write it and then we will see what it means. So in the equation that he gave is actually in 3 dimensions. Okay, let me actually give you the equation in full glory, and then we can trim it down to what we want to do it. So in Cartesian coordinate system, so this is partial derivative with respect to x, double derivative. So partial derivatives, for those of you who don't know, but I think most of you know because of phys lab, it's that when you are doing derivative with respect to, let's say, x of something, you know this is 3x squared, but when you have something which is a function of more than 2 variables, this partial simply means that other than x, everything else is treated constant. So this y remains y, and you take derivative of x. So similarly, the partial derivative with respect to y of this thing is x cubed, because this is treated as constant and y's derivative is 1. So partial derivative means when you have a function which is function of more than 1 variable, you can find derivative with respect to each one of them at a time. So he gave this equation. So I'll explain it in a little bit later time. So this is x, y, z, t. So here's the t as well, and this is equal to iota h hat partial psi by partial t. This is capital psi, p is silent. So this is the equation that he gave, that in 3-dimensional space, if you want to find the wave function associated with any particle, you have to solve this equation. The only thing you need to know to solve this equation is this, what is called potential. But the more accurate name that you are familiar with is actually potential energy. So instead of saying potential energy, we will just say potential, but it is the potential energy of a particle. So if you are given the potential energy of a particle, you put in here, and if you know some mathematics, you can try to solve this analytically by hand, but of course you can always solve this equation for several situations on computer and find this unknown wave function, which is the function of x, y, z and time. And once you have the wave function, you can find the probability density of particle by simply multiplying this function with its own conjugate. And conjugate is nothing but when you replace iota with minus iota. So once you have this probability density, you can find the probabilities in given region. Let's say you want to see what's the probability of finding the particle from x is equal to a to x is equal to b. All you do is integrate this psi square from a to b, and you find the probability of finding the particle in a given interval. So this is full three-dimensional equation. In this course, we will not be working mostly with this three-dimensional equation, but we will mostly work with one-dimensional equation. Now, before I come to this equation, I want to actually say a little bit about this potential. Then I'll come back to this. So far, you are used to specifying a problem using forces, right? If I want to give you a mechanics problem, I will specify the forces acting on a particle. For example, for a spring mass system, let's say you have a spring mass, and let's say this is x is equal to 0 point, and this mass is oscillating attached to a spring of spring constant k. So you solve this problem using Newton's law, right, in Mechanics 101. And to apply Newton's second law, what you need? You need force. So force for a spring, you are told several times that it is minus kx because it's proportional to x. So when the particle is here, the force in this direction, right? And when the particle goes here, this spring pushes it back. So if I plot this force, its plot looks something like this. It's negative in this direction and positive in this direction. So this is your f of x for spring, right? It's negative when it is extended, negative because the force is acting along minus x-axis, and it is positive when the mass is on this side. So this is how you are specified a problem. But in this course, we will not be specifying problems with the force, but with an equivalent way. And the equivalent way is specifying the potential energy associated with this particle. And what's the potential energy of this particle? Its potential energy is u of x half k x squared. And you can always find force from potential energy as f of x minus partial u by partial x. Because if I take its derivative, we get 2 here and kx and minus, so we get minus k. So this is the convention of this minus sign. So potential energy is nothing but giving you force, except that instead of giving it directly, it gives us through the derivative. Okay, so this is equivalent. If you are told the force and you solve the problem, this is completely equivalent to a problem where you are given a potential energy and you are asked to solve a problem. Because from potential energy you can find force by derivative, and from force you can find potential energy by integrating. And because of older convention, this negative sign is there. So it means if I draw the potential energy formula, the graph is something like this. So this is u of x. So potential energy is higher here, potential energy is higher here, and it is the lowest at the central point. And then again there is this point. For this lowest point, it doesn't matter what energy you assign to it. Usually we will assign it 0, but it can be here, it can be here, because between 2 points it's the energy difference which matters and not the absolute energy itself. So, if you want to find the wave function associated with a mass attached to a spring, all you do is take this u of x, put it here, and then solve this equation for psi. So how do you solve it? That's a separate issue. So once you have the psi, you can find the probability densities by taking the mod square, and from the probability densities you can find probabilities by integrating over intervals. So this is the general scheme of working with in quantum mechanics. Now, in this case, let me actually give you a couple of more potentials. Suppose we have a situation where we have a mirror here and a mirror here, and there are photons which are bouncing like this. So there are some photons, it's light, so you know when light goes to a mirror it gets reflected. So it goes there, comes back, comes here, it gets reflected, goes back. Or आप इसको ऐसे भी समझ सकते हैं, let's say these are two perfectly reflecting walls. Let's say you are in space station, at the International Space Station. अगर आप वहाँ से एक तरफ से ball throw करेंगे, the ball will go there, reflect back, come here, then reflect back, come there, and it will keep going like this. If you want to specify this problem using your old mechanics knowledge, what you will say, okay, when the ball is here, this ball exerts a force in this direction, right? It pushes the ball back. And when the ball is here, this ball exerts a force in this direction. But when the ball is here, there is no force. When the ball is here, there is no force. That's why once it is reflected, it goes on in a straight line with a constant speed unless it reaches here. Then reflects back, the force happens only here. And then reflects back and continue with constant speed and so on. So you can specify the force actually like this. If this is the x-axis, you can say the force here is like this. Actually, like a delta function, it goes to almost infinity. And then here, it's like this. So it's negative, so I draw a negative delta. There's a large force in this direction. But if you want to specify this problem using the potential, we can do it very easily in the same fashion, that the potential is something like this. Let's call it some V naught. So it means the potential here is 0, the potential here is constant, but here the potential is changing. And you see, यहाँ पे potential की slope positive है, तो positive slope का मतलब है, yes, आप सब लोग समझते हैं derivative gives us the slope of the function? Yes. Okay, good. So ये देखिए मैंने इस तरह से ड्रॉ किया है कि यहाँ पे इसकी स्लोप ऑलमोस्ट इन्फिनिट है, और जब कोई भी पार्टिकल यहाँ पे आएगा, it will feel this infinite gradient and will reflect back. And similarly when it comes here, reflects back. इसकी स्लोप नेगेटिव है क्योंकि यहाँ पे आ रहे हैं u के, so this is negative slope, and because of this minus sign, this becomes a positive force. And similarly here, the slope is positive, and because of the negative sign, force is negative. So you can specify this problem in this way. और समय इसको हम कहेंगे potential well, क्योंकि ये देखिए इसकी well की shape है, और बहुत सारे problem हैं physics में which deals with microscopic particle that actually can be modeled with the potential well. Even an atom, अगर आप बल्कि nucleus से शुरू करते हैं, what's a nucleus? Nucleus is almost like a trap for nucleons. एक न्यूट्रॉन इस तरफ को जाता है न्यूक्लियस की बॉल की तरफ, एंड की तरफ, it gets reflected. Reflected इस सेंस में कि वो जो different nucleons हैं, they attracted back. And once it is inside, हर तरफ almost same nucleons हैं, they are pulling it in every which way with the same force, so it's almost like free. Once it goes to the wall again, it feels a strong force inward again. So a particle is trapped in it like this. And not just the nucleon, many other particles like we can picture beta decay and other things, we will see in detail in the same fashion. Similarly, an electron is sort of up to like a zeroth order approximation. You can picture an electron in an atom like an electron in a box when it is when you have many electrons. Similarly, if you construct a diode, आपको पता है सब लोगों के पास मोबाइल फोन में डायोड्स हैं, which emit lights, जो फ्लैश करते हैं, there are several LED lights. ये सारी LED lights जो हैं अब बनती हैं इस तरह से that you have a thin material which is, and some other material on the other side, and the electrons trapped inside the thinner material, they're almost like in a van. Similarly, if you have a situation where you have, let's say, a capacitor plate which is positive here and positive here, and you have some proton here. So this proton sort of is trapped. This proton is trapped inside this potential well, because when it is far away from the wall, it's almost feeling like no force. When it goes here, it encounters the reflection and so on. So इसके अलावा और बहुत सारे problems हैं which can all be pictured like these potential wells. Usually potential well practice में there are more than one dimension. For example, अगर आप imagine करें एक small ball और ball की जो radius है वो 5 nanometer. We call it quantum dot, and you will learn why we call it quantum dot. So उस ball के अंदर जो free electron है, it's almost like trapped in a potential well. अगर कि वो 3-dimensional potential well है, ठीक है, क्योंकि वो इधर को भी बाहर जा सकता, इधर को भी बाहर नहीं जा सकता, इधर को भी बाहर नहीं जा सकता. So that quantum dot is also like a 3-dimensional potential well. जी? Yes, we will come to that. So lot of situations can be modeled with this potential well. Okay, so let's get back here and we proceed from here. I'll actually push this board up because I want you to be seeing this equation in the whole lecture today, so much so that you can remember it by heart. So let's now approximate it for one-dimensional problems. तो इस कोर्स में हम ज़्यादातर वन डायमेंशनल इक्वेशन से काम करेंगे और उसके रिजल्ट्स जो हैं वो मैं क्वालिटेटिवली आपके सामने जनरलाइज करूँगा, क्योंकि क्वालिटेटिवली दे आर एप्लीकेबल टू 2 and 3 dimensions in the same way. The only thing that would be different would be the numbers. The concepts remain the same. So in one dimension, this equation becomes minus h cut square 2m partial square psi of xt only partial x square plus u of x only. Just for the sake of completeness, in general, जो potential है, it can be function of time. जिस तरह फोर्स है वो कभी कम हो सकती है, कभी ज़्यादा हो सकती है, ठीक है. लेकिन इस कोर्स में we will treat only those problems in which the potential is fixed, like the force is constant with time, it's not changing with time. जी. नहीं, क्योंकि जो force is coming from the derivative of the potential. So the potential graph should be such that if you take its derivative, you should get the force. तो बिल्कुल ये देखिए, जैसे ये जो पैराबोला सा मैंने बनाया है, इसका मैक्सिमम पोटेंशियल वो इंफिनिटी x उस पे है, एक्सट्रीम पे, ओके. सो ये जो स्ट्रेट लाइन है, दिस इज द फोर्स and this bold type is the potential. So for this graph, you see there is a potential change here, so the force is only present here, and the potential change here, so the force is present only here. अब photon जो है जो मिरर के दरमियान जा रहा है, जब मिरर के दरमियान है, there is no force, so the force only acts when it reaches the mirror. Potential या force? क्योंकि पोटेंशियल जो है ना उसकी वैल्यू हमें फोर्स नहीं देती, Potential में जो change है, that gives the force. So if you have a constant potential, it means there is no force. अगर चाहे वो भी, there is a 10 volts potential continuously, it's not giving us any force because it's a constant. अब जैसे देखें, यहाँ पे मेरी जितनी potential energy है, it's the same जितनी यहाँ पे है. Potential energy तो है, but there is no force in this direction. क्यों? क्योंकि there is the same potential energy. लेकिन जैसे ये चार्ट है, यहाँ पे potential energy ज़्यादा है, यहाँ पे कम है. So there is a force in this direction, right? So the force only comes into play when the potential energy change. So this is an important question. Okay, thank you. जी. So इस problem में it doesn't matter because it gets reflected there, but in some problems it would matter, and we will study separate problems like this. Yes. Okay, so we will see that what we are actually doing here is something called stationary states, in which the things are independent of time. But जैसे मैंने शुरू में कहा, unfortunately इस course में we are not going to be studying those problems where we have to study the change in wave function with the passage of time. Okay, so for one dimension, this becomes xt is equal to iota h cut partial psi by partial t. Okay, so let's solve this equation, and we are going to solve it only once, and that is now. So please follow it, because what we get from here is something that we will be working with throughout the course. So this is Schrodinger equation, which is both space and time dependent. So this equation has several types of solutions. One of those types of solutions are called separable solutions, and we are only going to be dealing with those. So these separable solutions are solutions where we can write the wave function psi xt as a product of a part which is only dependent on x and a part which is only dependent on time. So in general, we can have something like x t square plus xt plus 3. But this is not a separable function. Separable functions are those where x and t part can be separated. For example, you can have x square plus 3x into exponential iota omega t or something like this. So we are going to consider only those solutions in this course which can be written as a product of x part and a product of t part. These are called separable solutions. These solutions, the other ones are too involved for us to go into. And they actually don't even admit analytical solution. We have to go to computational solutions for that. Okay, but fortunately, a large variety and almost all practical problems are covered by this type of functions. And whenever people have proved it, whenever we have a potential which only depends on x, we can always get separable solutions. Okay, so let me now substitute this one in this equation. So we get minus h cut square 2m partial x square. So this is small psi, this is capital psi. This only depends on x. Psi of x, phi of t plus u of x, psi of x. This is the same this Schrodinger equation. Just मैंने ये जो suppose किया solution इसको substitute कर दिया. So I suppose that this solution can be written as a product of this part and this part. इसकी वजह यह है कि this will admit us solutions which have practical applications. And this is also the simplest type of solutions that we can get from this equation. But लेकिन हम जो इसलिए नहीं कहते कि simplest, actually इसलिए भी कहते हैं that these are also the most important one. जो ज़्यादा complicated solutions हैं, they are also constructed using the sums of solutions of this type. हो सकती है. No, space-time will provide a solution of this equation. There are some situations in which solution can be written as the product of the two. And in the important thing is that even in those situations where you cannot write this solution as the product of the two, you can write that solution as a sum of several solutions of this type. For example, you can write psi1, phi1 plus psi2, phi2 plus phi3, phi3 and so on. So this is a sort of a building block of solutions. Okay, so from this, इसका solution हमें wave function बताएं. That is one information that we get out of it if we take its modulus square. कौन से वाली? So we will see that that also comes from here. So this is the derivative. Now you see the derivative with respect to x. So ये जो time dependent part है, this can be taken out of the derivative. और चूंकि ये डेरिवेटिव सब इसी का रहेगा, I can write it as d square dx square psi of x. जो डेरिवेटिव होता है ना, अगर तो फंक्शन एक से ज्यादा है अंदर वेरिएबल, तो we write partial. जो ही जैसे ये टाइम डिपेंडेंट पार्ट में बाहर निकाल लिया, आप इसको बेशक पार्शियल स्क्वायर में पार्शियल x को लिख लें, that is also perfectly fine. But there is no need to write that because now what is left inside is only function of x. So this is still u of x, psi of x, phi of t. Similarly, this doesn't depend on t, so I can take it out of the derivative and write as psi of x, and I can write this as d by dt instead of just partial t.
So how you compute the separable solution?
That's what I'm going to do now. वो गलती से ऊपर t लिखा हुआ है, the t is there. Okay? Okay. So from this equation, let's divide this last equation everywhere by this thing. So divide by psi and phi. Okay, so last में मैंने ये किया, ये देखिए, ये डेरिवेटिव विद रिस्पेक्ट टू x, एक x पार्ट है, एक t पार्ट है. So डेरिवेटिव तो चूंकि विद रिस्पेक्ट टू x है, तो ये मैं बाहर निकाल सकता हूँ डेरिवेटिव से. Because कोई बात नहीं, डबल डेरिवेटिव है, लेकिन दोनों विद रिस्पेक्ट टू x ही है ना. हम सॉल्व करें तो फंक्शन आएगा. So we haven't even specified the differential yet. Okay, so when we specify u, we will find it. So let's divide by this, and we get minus h cut square over 2m 1 over psi of x partial b square. So right now I'm not solving any particular problem. What I am doing right now is applicable to all problems. That's why मैंने कहा था कि इस इक्वेशन को इस कोर्स में हम एक ही दफा सॉल्व करेंगे. Because what I am doing is valid for all u of x so far. So once I start solving for u of x, that would be for special problem, and that would, in that case, we will also find the wave function. So I'm just trying to simplify this equation right now. So I divide by this, and we get u of x, and I get I of h cut phi of t d phi of t by dt. So मैंने उससे डिवाइड कर दिया जो वहां पे लिखा है. थोड़ा दिमाग भी इस्तेमाल करिएगा इस सवाल से पहले. Okay, so we have this equation. And we have obtained this equation, but if you look at the left side, we say that everything is function of x. And on the right side, we say that everything is function of t. So when you have two functions which are in general a function of, let's say, one variable and function of the other variable, and we say that they have to be equal. So what's the possibility of them to be equal to? Bit आपके पास मैं कहता हूँ f of x, there is some unknown function f of y, this is equal to some g of z. So if they are two equal, can there be some y in this function? क्या ये फंक्शन y स्क्वायर प्लस 2 हो सकता है? नहीं हो सकता, क्योंकि देखें ये राइट साइड पे z का फंक्शन है, तो कैसे y स्क्वायर प्लस 2 फंक्शन ऑफ z के बराबर हो सकता है? और इसमें मैं z नहीं डाल सकता क्योंकि आई एम सेइंग दैट इट्स ओनली फंक्शन ऑफ y. So there is only one possibility, and that is, let's say this is some constant c. Okay, both of these functions have to be equal to a constant, because then they would not be equal for all values of y and z. Anyway, this is just some constant c. So इनका ये सवाल है कि ये y स्क्वायर प्लस 2 z की इक्वल क्यों नहीं हो सकता? तो अगर तो आप किसी स्पेसिफिक वैल्यू ऑफ y और z के लिए ढूंढ रहे हैं ना, then this is a possibility, right? Excuse me, अब दोनों आगे बैठ के शुरू से बातें कर रही हैं, I'm trying to ignore it, so I get disturbed. So maybe कि आप इससे बाद में समझ लें. You can do this favor. Thank you. So ये जो चीज है, ये किसी स्पेसिफिक वैल्यू ऑफ y और z के लिए तो हो सकती है, बट नॉट फॉर ऑल z एंड फॉर ऑल y's. अगर मैं y 10 लेता हूं और z 7 लेता हूं, फिर तो बराबर नहीं होंगे ना. लेकिन अगर मैं ये कह दूं कि दिस इज आल्सो इक्वल टू 3 एंड दिस इज आल्सो इक्वल टू 3, देन फॉर ऑल वैल्यूज ऑफ z इन द वर्ल्ड एंड फॉर ऑल वैल्यूज ऑफ y इन द वर्ल्ड, दिस इज दे आर बोथ इक्वल. So it means, और ये जो हम मतलब मेथड सीख रहे हैं, some people don't even learn in PhD. So if you're not getting it, I'm fine with that. So इसमें हम, of course, they don't have PhD in physics or math. Okay, so I'm not talking about a PhD in physics or math. Of course, people in chemistry, they should also be able to know this thing. Anyway, so अब यहाँ पे देखिए हमने उसी इक्वेशन को इस तरह से अरेंज कर दिया है that I have two parts which are function of two different things. So it means there is only one possibility now, and that is that they both should be equal to some constant c naught. अब चूंकि c को स्पीड समझते हैं, let me, and I'm now going to find what this c naught is, and also from here it means instead of 1, I now have two equations. Number 1 is minus h cut square 2m 1 over psi of x d square psi of x dx square psi, and u of x is equal to some c naught, and a second equation iota h cut phi of t d phi of t dt is equal to c naught. So अब देखें, जब हमने ये अस्यूम किया तो उसका हमें फायदा ये हुआ है कि इंस्टेड ऑफ सॉल्विंग वन पार्शियल डिफरेंशियल इक्वेशन इन टू अननोन टू वेरिएबल्स, वी नाउ हैव टू ऑर्डिनरी डिफरेंशियल इक्वेशंस इन ओनली वन वेरिएबल ईच. सो दिस इज लाइक अ सिंपल डिफरेंशियल इक्वेशन दैट यू आर यूज्ड टू वर्किंग विद ओनली इन वेरिएबल x, एंड दैट इज अनदर सिंपल फर्स्ट ऑर्डर डिफरेंशियल इक्वेशन ओनली इन टाइम. यहां तक आप ओके. सो आर्गुमेंट ये है कि ये लेफ्ट साइड पे है इट्स फंक्शन ऑफ सम x and that is the function of some time t. So if they both have to be equal for all x and for all t, then there is only one possibility, and that is that they both equal a constant. Because if they're not equal to constant, they can only be equal at some specific value of x and t. So from this we now get two equations, because this is equal to c naught, this is equal to c naught. तो इनको जो separable solutions कहते हैं, उस मेथड का नाम है मेथड ऑफ सेपरेशन ऑफ वेरिएबल. It is because we are now able to separate one equation into two simple equations. Okay, so let me first solve this equation, because most of you can solve it quickly, because I can write it like this, right? d phi by phi, this is equal to c naught over आयोटा एच कट, अगर इसको दोनों तरफ इंटीग्रेट करें तो क्या आता है? So there is a dt here. So ये जो dt है इसको मैं उधर ले गया हूँ, ये आयोटा का इधर ले गया हूँ, और ये फाई नीचे गया, ठीक है? इसको अगर इंटीग्रेट करें दोनों तरफ, so I think you might have studied this thing that integral of 1 over x is ln x, right? So that's what I'm using. So this is d phi over phi. So if I integrate on both sides, we get ln phi, and on the side we get c naught iota h cut t plus some constant c1. So this means that log of phi, ये iota को ऊपर ले जाते हैं तो ये माइनस iota लिख देता हूँ, ठीक है ना? क्योंकि अगर ऊपर नीचे आप iota से मल्टीप्लाई कर दें तो नीचे iota स्क्वायर होगा, तो iota स्क्वायर -1 होता है, तो माइनस आ गया। अब हम इस तरह कहते हैं दोनों तरफ एक्सपोनेंशियल ले लेते हैं, तो ये दोनों चीजें जो कि इक्वल है, इसका मतलब है एक्सपोनेंशियल ऑफ log phi should be equal to exponential minus iota c naught h cut c1. Exponential और log जो है they cancel with each other, so phi of t is, और ये इसकी पावर में दो नंबर ऐड हो रहे हैं, I can keep them separate, exponential c1 exponential minus iota, so there is a t here, and let's call this thing omega. ये जो c naught over h cut है ना, let's call it some omega. So this means that c naught is what? यहाँ तक क्लियर है? अब यहाँ पर मैंने दोनों तरफ एक्सपोनेंशियल ले लिया, so ये log एक्सपोनेंशियल कैंसिल हो गया। अब ये एक्सपोनेंशियल की पावर है इस तरह से, so let's say you have x power a plus b, this can be written as x power a x power b. तो ये मैंने नया वेरिएबल खुद से इंट्रोड्यूस कर दिया, बार-बार c naught over h cut लिखने से मैं तंग आ रहा हूँ, तो मैं कहता हूँ let me call it some number w. So I called it some number w. So no, that's what we have. And now यहाँ से c naught की वैल्यू in terms of w जो है वो बनती है h cut omega. So this thing is some constant. Because this is exponential power constant, this is another constant, let me call it some c2 minus iota omega. So हमारे पास solution आ गया, और इसमें ये जो omega है, this is sort of an unknown thing because c naught is unknown, right? लेकिन आप यहाँ से एक चीज appreciate कर सकते हैं कि अगर हम अपने पिछले experience की तरफ जाएं, so this c naught seems to have the dimension of energy, क्योंकि c naught is h cut omega, right? So h cut omega we know is the energy. So अगर इसको आप energy ना भी कहें, तो this has dimension of energy. So in some books अगर आप देखेंगे, तो actually what they do that they simply call that constant E and then work out from there. अब देखें ये तो आ गया ना एक्सपोनेंशियल, इसको W कह लें, जो मर्जी कह लें, तो T के साथ जो भी होता है वो फ्रीक्वेंसी होती है ना, क्योंकि एक्सपोनेंशियल आयोटा ओमेगा T कोसाइन ओमेगा T या साइन ओमेगा T बनेगा, तो T का कोएफिशिएंट एंगुलर फ्रीक्वेंसी होती है, तो अगर ऑसिलेशन निकालो उससे पीरियड वो चीजें आ जाती हैं. So it means that this C naught is h cut omega, and the second equation which is minus h cut square 2m d square psi by dx square c naught psi. ये जो इक्वेशन है इसको मैंने यूं करके लिखी. अभी ये इक्वेशन सॉल्व नहीं की, सिर्फ ये वाला पार्ट सॉल्व किया. सो अभी अब हमें इस वक्त कोई जरूरत नहीं है कि दिस इज ये एनर्जी है कि नहीं है, बट this looks like an energy, but we don't even need to call it right now. So let's just think that this is a constant. Okay? अब ये वाली जो इक्वेशन है, I can solve it. because there is an unknown potential u of x which depends on a specific problem. So अगले हफ्ते डेढ़ में हम इसको 3-4 तरह के प्रॉब्लम्स के जो u हैं उनके लिए सॉल्व करेंगे. But before we do that, we need to know how the solution is going to look like and what are its properties and what we can get out of it. So to do that, let me just see that this general solution, capital psi of xt, this can be written as now small psi of x, which we don't know. Okay, we are going to find it for different problems. लेकिन जो time part है, that is not completely known. For all separable solution, that part is fixed because that is independent of u. और उसके साथ एक constant है और एक उसके साथ है minus iota expect नहीं minus iota omega t. इसके constant भी है c naught तो c2 जो है sorry. So let's assume that that's part of this function because this is still an arbitrary thing and we can put a constant here. So the separable wave function for all problems is going to look like this. और अगर आपने किसी जगह पे probability density find करनी है तो जिस तरह हमारे पास तरीका है psi mod square is equal to psi xt into conjugate psi xt. लेकिन अगर मैं इसको यहाँ पे put करूँ so I get psi of x exponential minus iota omega t psi star of x exponential plus iota omega t and this is psi of x psi star of x because this minus and plus they go away so this is nothing but psi of x mod square. So it means for separable solutions क्योंकि मैंने जब इसका conjugate लिया तो इसका conjugate और इसका conjugate हुआ. So इसका मतलब है कि instead of working with the full wave function of xt for these separable solutions and separable problems, we can just work with psi of x if our interest is just to find the probability densities. And another important conclusion from here is that the probability for these types of problem is independent of time. Because when I computed the probability density here by modulating, by taking the modulus and square, I find with only the square of the psi of x and time part is gone. So that's why the solutions of these types of problem, they are called stationary states. Stationary because their probabilities don't change with time. So that's why, and that part of the problem where we can study actually how the wave function change. Unfortunately, we will have to leave it to advanced class. I'll see actually if I can do little simple things regarding that or not. So the solutions of the one-dimensional problem for separable wave functions are called stationary states because the probability, not the function itself. याद रखें, जो wave function है, वो x और t दोनों पे depend करता है. लेकिन जो probabilities हैं, they only depend on the spatial part for these types of problems. So that's why we call the solutions of these problems as stationary states because they don't change with time. We can sort of say that, but it's more than that because जब stationary wave of कहते हैं ना, you imagine something like this. So for these wave functions, we don't imagine anything because they are not directly observable. What we observe are the probabilities. नहीं, अगर लेकिन कुछ ऐसी सिचुएशन हो सकती है जिनमें टाइम पे डिपेंड कर सकते हैं, that's perfectly fine. For अगर आप single slit experiment की बात करें ना, if you really want to solve it rigorously using quantum mechanics, it's actually a time dependent wave function. If you want to follow the particle along. हाँ, stationary with the dot. So probabilities are not in time or space. Probability density only comes from here. So when I talk its modulus is independent for it means you can compute probability in time, but it's constant because it's independent of time. अच्छा, आप कह रहे हैं ये कैसे निकालना? So I actually don't want to go to the calculus to prove this formula. For now, we can just assume that this formula is true. अब इसकी जो proof है using the limits and Riemann sum you can see in a book. Okay. And the second question, how this iota went up? What I did, I multiplied with iota here and multiplied with iota here. This is iota square, so it is minus. So I put a minus here. So that iota is here. So यहाँ मैंने ये किया कि ये हमारे पास separable solution है. अभी इसमें सिर्फ टाइम पार्ट हमें मिला है. जो स्पेशल पार्ट है, x वाला पार्ट, वो चूंकि डिफरेंट प्रॉब्लम में डिफरेंट होगा and we will find it for different problems. मैंने C2 डाला कि we can always we can put it here, doesn't matter, ठीक है? लेकिन आप उसको साई के अंदर भी समझ सकते हैं, ठीक है? So अगर आप probability density find करना चाहते हैं, you have to find its modulus square. उसके लिए आप इसको इसके conjugate से multiply करते हैं. इसको ये फंक्शन ये हो गया, इसका ये conjugate हो गया, तो टाइम पार्ट जो है वो खत्म हो गया. So essentially we have the square of the x part of the wave function. So that's why we call it stationary state, because probability densities are independent of time. So last question from this person and then we'll move on. इसलिए कि ये एक्सपोनेंशियल माइनस है, ये एक्सपोनेंशियल प्लस है, तो एक्सपोनेंशियल की पावर ऐड होगी. यहाँ तो खत्म नहीं हुआ, ये तो साई ऑफ एक्स की साई ऑफ एक्स की है. नहीं, ये मैंने यहाँ से यहाँ पे नहीं आया, ये यहाँ से वहाँ पे गया. दिस इज स्मॉल साइन, these are capital signs. Okay? Okay. I will do it maybe in the next lecture again, क्योंकि ये मैंने 2 दफा की है the same equation and I want to solve one problem. Okay. So now let's come to solving problems, and for that we have to find small psi of x, and today because of short time I'll do the simplest of all problems, and that is a free particle. So you can imagine a free particle as a particle in a potential which is 0. So let's say this is our u of x and the potential is 0. So this is the simplest problem. And let's say the particle has some energy E. So let's solve this equation, minus h naught square 2m d square. So the equation is, okay, so this is the equation, d square psi by dx square. U is 0, so that is gone. And this is C naught. Let me use E because that's what is commonly used symbol in this case. So this is this. So if I multiply with this part on the other side, we get d square psi of x dx square. मैंने C naught को E कह दिया, आप इसको C naught ही करें. Okay, so that's it. So it's like this. I'm solving this problem. Yes, I'm solving a problem of a particle in zero potential everywhere in the universe. So problem that we have a particle. Yes, that's an important question. Actually, it's even more important than solving the problem itself. Because अगर आपको problem का नहीं पता, so how can you solve it, right? So problem वो है जो मैंने वहाँ पे लिखा हुआ है. It's the problem of a free particle. Let's say you want to find the wave function associated with a particle which is free. And a free particle by definition is an idealistic situation. It's a particle in a universe where there is nothing else. So वहाँ मैंने कह दिया था ना. Now I'm trying to find it. So I'll prove that that's the case. There's only one particle in the universe. That's why the potential energy is zero. I'm finding its wave function. In quantum mechanics, when you have to find the information about a particle, you need its wave function. From the wave function, we can find its probabilities in different fields. आप लोगों की conspiracy तो नहीं आपस में? Okay, let's try to bog him down in asking the same question again and again. अच्छा. उनका क्वेश्चन है कि प्रॉब्लम क्या है, तो उन्होंने उसका जवाब नहीं सुनाओ कि बात क्या है. Okay, so let me repeat the problem. The problem is that we have a particle and the potential is zero, and we want to find its wave function. So this is our master equation given by found from the Schrodinger's general equation, which is only for the x part. Because t part अब मैं किसी problem के लिए find नहीं करूँगा. I have found it once, and for the whole course we are going to use this phi of t for all problems. The only thing that remains to be found is psi of x. अब इसको find के लिए हमें चाहिए क्या? U. इस लेक्चर के बाद जो different problem होंगे उनमें u जो है वो थोड़ा सा complicated function होगा. But let's begin from a problem where u is zero. So we have a situation where potential is zero. So what's the wave function of the particle? For that, I put this u0 in that equation, so I get this equation. So to solve this equation, I took this part and flipped it on the other side, and now I can bring this part to that side, because that's independent of u. मैं इसकी तरफ बाद में खिलाऊंगा क्योंकि let me do this part. So yeah, again, let's call this thing some k square. लेफ्ट साइड पे आके ये प्लस हो जाएगा. So we have this difference. I just क्योंकि ये इतनी सारी वो symbols हैं, तो I just I'm representing them with a one symbol like this. आप लोगों ने इसी क्वेश्चन का सॉल्यूशन किसी कोर्स में देखा होगा, कैल 1 या कैल 2? The solution of this differential equation. Okay. So I'm not actually going to find the solution. I'm just going to write the solution, but you can easily prove it that it is the solution. So the solution of this differential equation is psi of x, some constant a, exponential iota kx, some constant b, exponential minus iota kx. So I leave it to you as an exercise, voluntary exercise, that you just put this thing here and you will see that both sides are satisfied. पेपर में आ सकते हैं, नहीं आ सकते. It's not that difficult. कौन समझता है कि इसका सॉल्यूशन ये साबित करना है कि ये इसी का सॉल्यूशन है, मुश्किल सा काम. Okay, so let me do it. So to prove that this indeed is the solution of this equation, I need to find its derivative. So d psi by dx would be iota k, exponential iota kx, minus iota kb minus iota kx. Let's take it. ये जो solution है इसमें, तो इसका दोबारा डेरिवेटिव ले लें, माइनस k स्क्वायर a iota kx. इसका दोबारा से ले लें माइनस माइनस प्लस iota स्क्वायर माइनस k स्क्वायर b एक्सपोनेंशियल माइनस iota kx. नाउ आप ये देखिए, मैंने डबल डेरिवेटिव फाइंड किया उस सॉल्यूशन का. आप इसको और सॉल्यूशन को उसी इक्वेशन में पुट कर दें. यू सी कि वो k स्क्वायर है ना, उसका कोफिशिएंट तो साई के साथ उसको मल्टीप्लाई करो प्लस के साथ है, ये दोनों टर्म माइनस के साथ आई हैं, you will put them there, all terms will cancel out, it means that indeed is the solution of the differential equation. ये देखिए ये डिफरेंशियल इक्वेशन, इसका ये मैंने सॉल्यूशन लिख दिया. नाउ वी आर गोइंग टू ट्राई टू प्रूव दैट दिस इंडीड इज द सॉल्यूशन. और सॉल्यूशन हम कैसे प्रूव कर सकते हैं? अगर हम सॉल्यूशन को इक्वेशन में पुट करें तो लेफ्ट हैंड साइड राइट हैंड साइड के बराबर आनी चाहिए. सो उसके लिए मैंने क्या किया, उधर दो टर्म्स, एक साई है एक साई का डबल डेरिवेटिव है. मैंने इस साई के डबल डेरिवेटिव निकाल लिए, पहले एक दफा डेरिवेटिव निकाला फिर दूसरी दफा निकाला. तो नो दिस इज द डी स्क्वायर साई बाय डी एक्स. अगर आप इसको और साई को इसमें पुट करें तो लेफ्ट साइड पे चारों टर्म्स कैंसिल हो जाती है आपस में. So it means left side is 0, right hand side is 0. So this thing is indeed the solution of this differential equation. जी. नहीं ये k एक ही है ना, ये वाला k, ये k, ये सारा एक ही k है. ये k यही वाला k है, उसी सूरत में तो ये फिर बैलेंस होगा. ओके, सो दिस इज जी ये कहां से आया है? देखिए इसको डेरिवेट किया तो ये आयोटा क्या आया, फिर तो आयोटा स्क्वायर माइनस आयोटा स्क्वायर माइनस 1 होता है. सो नहीं ये उसके इक्वल नहीं है. अगर इसको उस पे पुट करें तो सारी टर्म्स कैंसिल होती हैं. यू कैन डू इट. ओके, सो दिस इज द साई. अब देखें अगर ये साई है तो कैपिटल साई क्या होगा? सो इट मीन कैपिटल साई ऑफ एक्स टी व्हिच वाज साई ऑफ एक्स इनटू फाई ऑफ टी इज नाउ, ये साई है और फाई कहां पे है? ये फाई है. इस फाई और उस साई को यहां पे पुट कर दे, यू विल गेट सम a1 एक्सपोनेंशियल आयोटा kx minus omega t plus some b1 plus omega t. So this is the wave function of a free particle. और जो a1 है, this a1 is a into c2, और जो b1 है दिस इज b into c2. ये वाला नहीं, ये मैंने प्रूफ किया क्योंकि ये देखें ये हमने सॉल्यूशन इस तरह अज्यूम किया था ना शुरू में. तो अब मैंने जो साई फाइंड किया है फ्री पार्टिकल, ये वाला साई और ये फाई ऑफ ई जो सबके लिए वैलिड है, ठीक है, वो दोनों साई और फाई मैंने यहाँ पे रखे और इनको मल्टीप्लाई किया तो ये दो टर्म्स आ गई. क्योंकि इसमें एक ही टर्म है तो इसकी दोनों टर्म से बारी बारी मल्टीप्लाई हो जाएगी. अब ये देखिए ये क्या है? दिस वी ऑलरेडी नो रिप्रेजेंट्स फ्री पार्टिकल. एक्चुअली आई जस्ट स्टेटेड एंड शोड बाय इंस्पेक्शन बाय वर्किंग विद कोसाइन एंड साइन वेव्स दैट अ फंक्शन लाइक दिस represents a wave. So essentially this represents a free particle which is moving this way, and this part represents a free particle moving this way where this a1 and b1 are arbitrary constant. So अगर आप a1 0 ले लें, you have a particle moving along negative x-axis. if अगर आप b1 जो है ना वो b1 0 ले लें, you have a particle moving along positive x-axis. So अगर आपके पास एक free particle है universe में and you are in one dimensional universe that it only has one axis, you can either move left or you can move right. And since there is no force, क्योंकि u zero है, if there are no forces, what do you expect? If a particle is going left, it has to continue to go to left. If it is going right, it has to continue to go to right. And that's what this equation is also telling us. Plus, अब यह है यहाँ पे आप proof भी देखे हैं कि initially we just stated that a free particle is represented by a wave function like this or like this. Now we know that where it comes from. Actually, जिस तरह से हमने किया है, this was also the part of evolution of human thought. 1900 से लेके 1930 तक ये इक्वेशन श्रोडिंगर की 1926 में आई थी. people were struggling. Initially, when in 1915, after de Broglie's hypothesis, and in 1920s by electron diffraction experiments, people had this idea perfectly crystal clear that particle behaves like waves. And for free particle, they can, since people had experience with plane waves, that they can be represented by plane waves. But for general situations, how do we find a wave function? What wave function gives us prediction that agrees with experiments? Several people started doing work on them, and Schrodinger and Heisenberg came up with the way of finding those wave functions, and one of that was this Schrodinger wave equation. And here we just saw a little glimpse of that success of the equation in finding the wave function of free particle. In the later lectures, we will see that this equation can be used to find wave function for complicated problem and that agrees with experimental results. Yes, please. Because let's say if A1 is 0, that we have a particle initially moving in this way. So you see, this is something which represents a wave that will continue for eternity. Because there is no change with time. It's periodic in time, it's periodic in x. जी? नहीं, अच्छा यहाँ पे आप बात समझ में उसका आपको जी आप अब मैं यहाँ पे थोड़ा सा एक चीज़ कमेंट करना चाहूँगा जो कि शुरू में अक्सर स्टूडेंट्स की कंफ्यूजन का बायस होती है, वो है मैथ एंड फिजिक्स एंड व्हाट्स द कनेक्शन बिटवीन दैट। जब आपके पास एक इक्वेशन है, स्पेशली डिफरेंशियल इक्वेशन, ठीक है, आप उसको सॉल्व करते हैं, जो सॉल्यूशन है दैट कैन हैव सम आर्बिट्रेरी कांस्टेंट, दैट फॉर ऑल वैल्यूज ऑफ द कांस्टेंट द इक्वेशन इज सेटिस्फाइड। फॉर एग्जांपल, फॉर एनी वैल्यू ऑफ a and b, this psi is solution of this equation. So this is math. Math tells us that there are infinite number of possible equations that satisfy this equation. For example, you can have a10, b0, a20, b0, a0, b10, a0, b30, a0, b iota, or a1, b1, all of them. Now, what is the value of a and b that we have to choose? That tells us, that is told to us by the physics of the problem. We have to choose those values of the constant that satisfy the physical problem. Mathematics will give us all solutions, including physical and non-physical. Okay? So it's the common sense that we have to use, and we will actually develop a systematic way of finding these unknown constants. For now, since the particle is free, it can either go this way or that. That's the only possibility. Even being stationary is part of one of them. We can take k infinite or omega infinite and it will, let's say, be there. So that's why if the particle is free, either this is 0 or that is 0. और अगर इस तरह का problem फर्ज करें जब mirror वाला आएगा, we will see that equation that has to be satisfied the same. Actually the solution is also of the same type. And we find constant in such a way that corresponds to the physical part. In the last 2 minutes, I just want to come to this equation to tell you only two things, and that is absolutely important. Whatever problem you solve, your psi should always meet two conditions. Number one, that the probability of the finding of the universe, of the particle in the whole universe should always be 1. आप एक प्रॉब्लम सॉल्व करते हैं और साई निकलता है, तो वो साई ऐसा नहीं होना चाहिए कि वो आपको यहाँ से यहाँ तक ये है कि इसके होने की probability 10 है या infinite है या 0 है. 0 is possibility, but 10, 20, that's not possible. So और अगर आपका जो साई है, आप पूरी यूनिवर्स पे probability find करें. For example, if you absolute square it and you integrate it over the whole universe, over the whole one-dimensional universe, your answer should always be 1. You should get a psi that tells you the particle is going to be somewhere in the universe. The second thing, which is actually imposed by the mathematics and not physics, and that is that अगर आप इस equation में देखें, तो अगर आपका u smooth है, तो जो आपका psi है, that should also be smooth. क्योंकि अगर साई स्मूथ नहीं होगा तो आपकी इक्वेशन जो है वो सेटिस्फाई नहीं होगी। फर्ज करें आपका साई जो है वो इस तरह का है, लेट्स से यू हैव अ साई लाइक दिस, so this is psi. You see, such a psi cannot satisfy this equation. क्यों? क्योंकि जब आप इसका डेरिवेटिव फाइंड करेंगे तो इस डिसकंटिन्यूटी की वजह से इंफिनिटी आ जाएगी, इसकी स्लोप इनफिनिट है ना, तो अगर आप एक डिसकंटिन्यूअस फंक्शन का डेरिवेटिव फाइंड करें इंफिनिटी आ जाती है, बाकी कहीं भी इंफिनिटी नहीं है। सो इट मीन योर psi should always, ये किसी तरह का भी हो, ऐसे चला जाए, यूं चला जाए, it should always be smooth. And smoothness includes that it should be single valued, क्योंकि अब नॉनसेंसिकल रिजल्ट नहीं आने चाहिए। ये ना हो कि आपका साई जो है वो कहे कि पार्टिकल यहाँ पे होने की प्रोबेबिलिटी 10 है और 20 भी है। टोटल should be 1. It should be somewhere. नहीं, वो तो है अगर आप किसी इंटरवल की बात करें, लेकिन पूरी यूनिवर्स में होने की प्रोबेबिलिटी 1 होनी चाहिए। Okay, so with this, let's end it here, and we will continue from here in the next lecture. Thank you. Oh, we have a survey, so please, before you go, just take your favorite question for homework.